Hey everybody, let's give this problem a try. So now we have a capacitor and this switch has been open for a long time. Okay, so if it's been open for a long time, that means the current and voltage everywhere is constant. Now for a capacitor, let me just label it here. So the voltage across over here, across this capacitor, right? So from here to here, it's constant. And the current going through a capacitor is C dV dt. Now if we're saying the voltage is constant, that means the time derivative is 0, right? So dV dt is 0, which means the current going through the capacitor is 0. So there's no current going through this capacitor. It's like unplugging it. Right, so then all that's left is this 5 ohm, 2 ohm, and then this we can just unplug, right? No current's going through there. What about this big mess over here? It's oftentimes helpful to use source transformations. Okay, so you see this node is over here. This node is over here. Why don't we do a source transformation? Okay, that switches here, right? So let's replace this with something here. So how do you do a source transformation? Instead of a current source and a resistor in parallel, it's a voltage source and that same resistor in series. So that's 20. And then how much voltage? IR. So 0.1 amps times 20 ohms is 2 volts. Right? Okay, and then just 2 plus 1 is 3 volts. Okay, so how much current is here? This is I2, this is I1. And if you just take a look at it, everybody has the same current, right? It's just going around this rectangle. So I1 equals I2 equals the current everywhere, going around the rectangle. Okay, and then what current is that? So this is before we close the switch, right? So I1 at 0 before we close the switch equals I2 at 0 equals V over R. 3 volts over 20 plus 5 plus 2 plus 3 is 30 ohms. Okay, so we got 0.1 amp. So there you go, that's part A. They're the same. Okay, but now after we close the switch, different story, right? So whatever current was going here, 0.1 amps, before, as soon as we close this switch, right, look, if we close this switch, this current goes right this way, and none of it is going to go this way, right? So none of this will get any current after we close the switch. Okay, so let me clean this picture and we can draw the capacitor again. Okay, and how about I just erase there? Okay, so this is after we close the switch. Now, the current here, okay, how about, let me rearrange this drawing. See this 5 ohm and 3 ohm resistor? Let me just draw it next to it. I'll draw it like this. So the 5 ohm and the 3 ohm combine to be 8 ohms, right? Okay. Now, the voltage, we said I never calculated it. What's the voltage across? No problem, right? The current here for the 2 ohm resistor here is 0.1 amps. So what's the voltage across the 2 ohm resistor? The voltage across the 2 ohm resistor is IR. So that is 0.1 amps times 2 ohms is 0.2 volts. That's the voltage from here to here, which is in parallel with the capacitor. So that's also the voltage across the capacitor. Okay, that's before we close the switch. And for a capacitor, the voltage cannot change instantaneously. So the voltage across the capacitor is still 0.2 volts after we hit the switch, right? This cannot change instantaneously. So that means for this picture, which is this picture, the initial voltage across from here to here is 0.2 volts. And it's the same for this resistor, the same for this capacitor, the same for this resistor. That being said, what's the current going for I1 over here? I1. I1 after is IR, V over R, sorry, right? So 0.2 volts over 2 ohms. Okay, so 0.1 amps. So that's this one over here. What about I2? That is going, I2 is like this way, right? Which is going this way, just according to the picture. So then what is I2? Just the way it's labeled with the voltage being this way. I would be minus V over R. Minus V over 8 ohms. Right, so this is different now. So 2 over 8 is 0.25, so minus 0.025. Okay, so it's different now, right? This compared to this. That current could change in a resistor instantaneously, no problem. The current can change through a capacitor instantaneously, no problem. It's just the voltage that cannot change across a capacitor instantaneously. And in fact, that is exactly why part C. Right, so that's why, because what I just said, the voltage across the capacitor cannot change instantaneously. But it could definitely change across through a resistor, right? No problem, as we see right here. Okay, and then now let's do part E and F. What's the current as a function of time? So we definitely can get the voltage as a function of time, because for the capacitor, squeeze right here. For the capacitor, it's V naught e to the minus t over RC. Okay, what resistance? This resistance would be, let me just see this picture right here. It looks like, let me go where there is more space. Okay, it looks like whatever the equivalent resistance of 2 and 8 in parallel. So whatever that is, 1 over 2 plus 1 over 8. Take the reciprocal. So 1 over 2 is like 4 over 8. So reciprocal of 5 over 8. So 8/5. So this is 1.6. Okay, so that's this value right here. And then the capacitor we knew was 2 microfarads. And then the initial voltage is 0.2. Okay, so we got this. That's the voltage from here to here. But then if you want the current, no problem. I1 is V over R. Right, so be careful. See the plus over here, minus over here, and then the way the arrow is drawn. So I1 is V over R. Right, so V naught e to the minus t over RC over 2 ohms. And then for I2, see how plus over here, minus over here, but the arrow is going the other way from minus to plus. So for I2, it's minus V over 8 ohms. Right, just because the way it's labeled. So just be careful with that minus sign. Okay, so then this is part E, and this is part F. Okay, keep on studying. I'll see you on the next video.